Bismillahirrahmanirrahim. Assalamualaikum and a very good afternoon. Okay, now let's have a look on the rectangular patch and equivalent circuit. So the equivalent circuit for the patch antenna is shown as in here. So in which there's two slots. So here is slot 1 and on the other side is slot 2. Alright, in which it is separated by a transmission line of length L with characteristic impedance YC equal to 1 over the characteristic impedance. Right, so the Y is the admittance. Okay, so the admittance equal to the conductance. G is conductance plus B is the susceptance. So it's something like the real and imaginary part. Right, so for rectangular patches, so the slot 1 and slot 2 is basically identical. So it is assumed that the admittance Y1 equal to Y2 and the conductance and also susceptance of slot 1 are equal to slot 2. Right, for infinitely long slots, assuming that the electric field is uniform across the slots, but valid only when the W is larger than the lambda naught and H is less than lambda naught. So the conductance and the susceptance can be calculated by using these equations. And the K naught here is the free space wave number. K naught is free space wave number, in which can be estimated by using 2 pi over lambda naught or equal to omega over C. Okay, while for extremely wide or narrow slots, since we are assuming that G1 equal to G2, so G1, the conductance is equal to the following equations depending on the width of the patches. Alright, so the input admittance Y of the structure or the patch is reduced to Y in equal to or approximately 2G1, 2 times of the conductance, while the input impedance Z-in equal to 1 over the admittance, input admittance, which is more or less equal to R-in, the input resistance, which is equal to 1 over 2G1. And when the mutual coupling between the slots is considered, so the total input impedance is equal to the total input resistance, which is equal to 1 over 2G1 plus minus G12. So G12 is the mutual coupling conductance between slot 1 and slot 2. From a previous slide, we have seen that the input resistance R can be controlled by adjusting the width of the structure, in which the input resistance is decreased by increasing the width. However, this method only limited to the ratio of W over L is less than 2, because the aperture efficiency may drops when the ratio between W to L is larger than 2. Another method to adjust the input resistance is by using the inset feed or recessed microstrip feed, in which we can control the position of the feed point. Right, so the inset feed distance is represented by Y0, in which it is basically the position of the insert feed to the edge of the structure, the edge of the patch. Okay, so basically by introducing the insert feed, we are basically introducing a notch or a junction capacitance on the structure, which may affect the resonance frequency of the patch antenna. Alright, so at the edge of the patch antenna, the voltage is maximum while the current is minimum, which yields to a higher impedance. Okay, so R in here is between 150 to 300 ohms. Okay, while when the feed points is moved towards the center of the patch, so at the center, the V drops while the current is at maximum, so yields in lower input resistance. Therefore, we can see that the input resistance of the patch antenna is strongly dependent on the position of the insert feed. Okay, mathematically, we can represent the input resistance by using this equation. This is the input resistance when at the edge of the structure, when y equal to 0, which is equal to 1 over 2G1 equal to 1 over 2 the intrinsic impedance 120 pi or equal to 377 ohm lambda naught and then divided by pi multiplied by the width. Alright, so for the input resistance when the insert feed point is varied, so it is equal to R in y equal to y naught, the new insert position. It dependent on the R in when the feed point is at the edge of the structure multiplied by cos squared by y naught divided by L. Alright, if in patch antenna design, usually we have targeted or required input impedance typically 50 ohm. So once we have set the input resistance, so we can determine y naught, the position of the feed point, to match the required or the intended input resistance. Okay, let's have a look on an example. A microstrip antenna with overall length equal to 0.906 L 0.906 cm, and then the width is 1.186 cm, and the height of the substrate H equal to 0.1588 cm. So I will prefer to list out all the information that you can pull out from the given statement or question, so it will be easy for you to refer to during the calculation. And the dielectric constant of the substrate is 2.2, operating at 10 gigahertz. And then given the G1 and G2 equal to those values, right? So G1 is the conductance at slot 1, 0.00157, while G12, due to the coupling effect between slot 1 and slot 2, 1.1683 times 10 to the power of minus 4. Right, so the question asks you to determine the input impedance at the input impedance. Okay, so you have the microstrip patch. So the L is there, and this is the W, and you need to determine the R in. It is not stated where about the feed position, so we assume that the feed position is at the edge of the structure, somewhere here. Okay, so you are given G1 and G12. So in this case, the input impedance Z in is equivalent to R in. Since you know the G1 and G2, so it is equal to one over 2 G1 plus minus G12. Alright, so and it is assumed that it is in TM010 mode with odd field distribution. So the plus minus sign here, so for positive is when it is odd distribution, and negative when it is a symmetrical distribution. Okay, so in this case, it is mentioned that it is odd field distribution, so you need to consider the plus sign. So in this case, the Z in is equal to R in equal to 1 over 2. Your G1 is 0.00157 plus the G12 1.1683 times 10 to the power of minus 4. So you get the R in equal to Z in equal to 228.35 ohms. Don't forget the unit. Okay, if G1 and G12 is not given, so you need to consider using the equation of considering the intrinsic impedance. Alright, next the question asks you to determine the input, the feed point position or the insert feed point position if the required input impedance is 50 ohm. Okay, so R input impedance, so R in when Y equal to Y naught. So now the insert feed point, meaning that the feed point has been moved from the edge to somewhere else at Y naught position. So in this case, it is equal to R Y equal to 0. So R in equal Y equal to 0 when the input resistance at the edge multiplied by cos squared pi Y naught over L. Okay, so since we have calculated the edge R in at the edge, so it is equal to R in at Y equal to 0. So the required impedance is 50, so R in equal to 50 ohm equal to R Y naught is from the earlier calculation 228.35 ohm cos squared pi Y naught over L, and L is given as 0.906. Okay, so from here you can get your Y naught, the insert position, which is supposed to be 0.313 cm. Okay, so to get the antenna match at 50 ohm. Okay. Okay, let's look at how the radiation pattern of microstrip patch looks like. So this is from the previous example with the parameters given. So we know that the patch antenna, you have the conductor on top, and then we have the substrate, and it is backed by metal ground plane. Okay, this is the patch and this is the substrate. Right, since there's ground plane at the bottom, meaning that the field is blocked or will be reflected once it reaches the ground plane. So the antenna will radiate in that direction. It is a directive broad radiation pattern for microstrip patch antenna. So in this case, if we cut the pattern, we cut this pattern in E plane. So E plane, we cut it somewhere here. So there's almost no signal at the bottom. So we can see that there's directive pattern on top. Alright, for H plane, when we cut the plane in horizontal plane, okay, and we look from the top, okay, so we will see there's shape, okay, there's a loop on top and some energy at the bottom here. This is due to the coupling at the feed point position. Right, this is in the H plane, and the directivity for microstrip patch antenna can be estimated by using this equation D2, meaning that for microstrip antenna there's 2 slots, and the general equation for directivity commonly for all antennas is D naught equal to U max over U naught, which it is dependent on the P rad and the radiation intensity. Alright, and the directivity dependent on the width of the patch, either it is larger or smaller than lambda. And in terms of the beam width, alright, in E plane it can be estimated by using this equation, and in H plane it can be estimated by the following equation. And K naught, as mentioned earlier, is the free space wave number equal to 2 pi omega over C. Okay, is also equal to 2 pi over lambda naught. Before we step in the next discussion on circular patch antenna design, so let's have a quick quiz too. So you need to try to solve these problems, and please make sure you write down all relevant equations, and please list down or clearly show your steps before presenting your final answer. And you need to submit the quiz 2 in the e-learning before or by 9th of January 2022. Okay, besides rectangular microstrip patch, there's another one, microstrip patch antenna that commonly used and popular in communication system, which is the circular microstrip patch antenna. So it is more or less the same as a rectangular patch antenna. However, the cavity or the shape of the patch is in a circular shape. Okay, as opposed to the rectangular patch antenna, so circular patch antenna, we treat it as a circular cavity for the patch and substrate. Right, so the cavity of circular patch consists of 2 perfect conductors or metal conducting materials on top and at the bottom. So on top we have circular shape of patch. It is a metal conductor, and another one is the ground plane also using metal conductor. Commonly used is the copper. and a cylindrical magnetic conductor around circular periphery. Okay, the perimeter of the circular is surrounded by a cylindrical magnetic conductor, and both layers, the top, the patch, and the ground plane, is separated by a substrate material. Right, if compared to the rectangular patch antenna, circular patch antenna use 1 degree of freedom to control the mode, which is the radius of the patch. Okay, if compared to rectangular, we have the W, the width and the length of the patch to control the modes of transmission. Okay, now let's have a look on the procedure or the steps to designing a circular microstrip patch antenna. So it is much simpler if compared to the rectangular patch antenna design steps. Right, so the first step is to specify the parameters such as the relative permittivity or the dielectric constant, the resonant frequency in hertz, and the thickness of the substrate in centimeter. Next, we need to determine the actual radius of the circular patch. So a circular patch, so we need to identify or to calculate the actual radius of the circular patch. Right, so we need to figure out the factor F by using this equation. So Fr is the resonant frequency, while this is the dielectric constant of the substrate, or the relative permittivity of the substrate. Okay, let's look at an example. So we have seen the procedure to determine the radius of the circular patch A. Okay, actually there's lot more steps in order to determine the directivity, the conductance of the circular patch. However, we just focusing on the main parameter in designing microstrip patch. For rectangular, we have determined the W, the width and the length as the control parameter to control the transmission mode, while for circular patch, only 1 degree of freedom, which is the radius of the patch antenna, is used to control the transmission mode. Right, so let's look at the example. Design a circular microstrip antenna using a substrate RT Duroid 5880 with a dielectric constant of 2.2 and thickness of 0.5188 cm and resonating at 10 GHz. Right, so this is the standard value for the dielectric constant and thickness of RT Duroid 5880. Right, so to solve this, the first thing is to have the general equation in hand. So based on previous slide, we have the A, the radius of the circular patch, given as A, as the following equations, and the F, the factor F, can be determined by this equation. So let's since the A dependent on the F, so we need to calculate the F first. So the F is 8.791 times 10 to the power of 9 divided by, so Fr given the resonant frequency is 10 GHz and the dielectric constant is 2.2, while the thickness H is equal to 0.5188 centimeter. Right, so divided by Fr is 10 gig and the square root of epsilon r 2.2. Right, so the F is equal to 0.593. Right, once we have the F, so now we can calculate the radius, equal to, so the F divided by 1 plus 2h divided by pi epsilon r f ln of pi f divided by 2h plus 1.7726, and all being square root. Okay, now let's include in the f values. So we have f equal to 0.593 divided by 1 plus 2. Your h is 0.5188 divided by pi epsilon r 2.2, and the f is 0.593. Okay, ln by f, your f is 0.593 divided by 2h. Your h is 0.5188 plus 1.7726. Okay, and don't forget to square root or to the power of 1/2. Right, so the f here, the a is equal to 0.525 cm. Okay, since you have seen lots of calculations, therefore I would recommend you to write down the equation first. The general equation. Okay, this is the general equation. Write down this one first, then include in all values, okay, into the equation before you have your final answer. Okay, why you need to include those steps? Because since it involves lots of calculations, okay, very long calculations. Therefore, if you have mistakenly press your calculator, okay, if you have something like mistakes during your calculation, so it will not so your final answer will be wrong. If you provide details in earlier steps, therefore you may score higher marks in the steps. Only you will only be penalized in the final answer. If you don't provide this and suddenly you just provide the final answer, you may have missed the final answer marks plus the steps marks. Okay, so in order to score, please ensure you have the general equation, have the values in the equations before your final answer. Okay, as similar to rectangular microstrip patch antenna, so the radiation pattern of the circular microstrip patch also having the directive pattern. So because it's still having the ground plane underneath the structure, right? So it is a broad beam width, okay, broadside directive pattern, okay, both in E and H plane, right? So this is the 3D presentation of the radiation pattern of circular microstrip patch antenna. Okay, with that, thank you. Please don't forget to complete your quiz 2 and submit it through the e-learning. Thank you.